All right, good morning. Let's start the lecture. All right, so we're going to go back to vector field today now. Okay, so we finished double integral, triple integral. Okay, has nothing to do with vectors. So now we're going back to the vector fields. And we'll start to do some integrations within these vector fields. Okay. Another thing I also wanted to point out, if you recall, I have repeated this a couple of times. The last couple of weeks of the lecture, the most important part of this course. And every time, unfortunately, by the time of this moment or this year, the tendency, you're the worst of the tendency. So somehow the human nature doesn't change. Every year, doesn't matter how many times I repeat, things happens as usual. So if you have been consistently coming to the lecture, congratulations, that's good, so keep it up, because the last 2 weeks are the most important part of the course. Okay. Okay, so let's talk about the vector field first. Vector field, even though this is sort of like a new concept you first heard of, it's actually not new. Okay? So basically, the keywords, it's a field, and it's a field represented by a vector function. Okay, by vector function. So what do we mean by a vector function? We have seen many vector functions before. In 2D, you may have a vector function So here's a vector function, right? Very typical. There are two components for this vector. I call it 2D vector function. It's a function of x and y, and then of course just have only x component and the y component. But both of the x component and the y components are a function of x and y. Okay? So that's called a vector function. Right? So try to relate to scalar function. Right? When you have a scalar function, that's what it looks like. Okay? So this is scalar. And in 3D, it's a vector function of 3 variables, x, y, z. So that's a 3D vector function, and you could extend to any dimensions you want, right? But we can only visualize up to the 3D here. Okay. So that's vector functions. Whatever function, scalar function, you can put it over here, and then you can construct a vector function. And then vector field is basically when you visualize this vector function, and it give you a field, and that's what we call the vector field. So for example, I'll show you a couple of things. Okay, let's take a look at a couple examples of vector fields and how we illustrate a vector field. So the first example, let's take a look at this one here. F equal to x I hat plus y j hat. That's a vector function. It's a 2D vector function. So x and y hat, x hat plus y hat here. Okay. So how do we visualize this vector field? This is how we do. First, you draw the xy coordinates, and then we'll start to basically put in the vector now, because this one essentially is a vector. When you're putting an x and y value into it, you got a vector here, right? So let's say, for example, if I put in x equal to 1 and y equal to 1 into this vector function, and I end up with what? I hat plus j hat. Right? So that's this vector function, give you this vector. And I hat j hat, if you draw this vector, right? So first we'll say, okay, here's a vector I hat plus j hat. Then you're required to draw it. So let's go draw this vector here. So what you do is you basically find, here's 1, and then this is 1, 1. So you draw the vector from origin to 1, 1, right? So this vector here is your I hat plus j hat. Is that good, right? But however, when this time we're plotting this vector field, so if you look at this one here, basically this is the vector at 1, 1. So this is how you should understand it. So this I hat plus j hat is the vector at the 1, 1 location. So what we need to do is we need to move this vector. Okay, instead of always starting from origin, start from 1, 1, and then draw this same vector in the same direction, the same length. Okay, so that's this vector I hat j hat at 1, 1 at here. That makes sense? Very much like the way you draw, if you recall that in assignments, you practice drawing what type of vector? The greeting vector, right? So if you have a function and you're required to sketch the greeting vector, so greeting vectors always draw at the certain particular point. Okay? And similarly, if I give you a point, let's say -1, -1. So let's say x equal to -1 and y equal to -1. And you draw the vector at this location. And for this particular vector function, you end up with -I hat minus I hat. Okay. So if I do the same process at here, I'm going to plot this -I hat, -j hat. But instead of plotting it starting from origin, we start from -1, -1. So you have basically another vector, right, pointing this way. Okay. Similarly, you can do -1, let's say -1, 1, or 2, 2. Okay. So if I do this, -1, 1, we get vectors over here. Okay. And 2, 2, you get a vector somewhere over here, and it's longer length, okay, pointing to that direction. Okay. So that's basically the way we're constructing this vector field. Essentially, it's a field consists of infinite number of vectors, right? So, and where's that vectors from? It comes from this vector function. So if you plot, you cannot plot all the vector out, right? You can only selectively plot some vectors to see the trend, basically. But if you plot enough out of it, right? So you end up with, for this particular one, okay, you end up with a whole bunch of vectors, like readings pointing out of the origin here. And at the far away from the origin, the vector length, right, it will be longer. So that's basically this vector field. Okay. And that's how you visualize this vector field. Okay. Let's take a look at another example. if we have another vector field, but this time let's slightly change this vector function. It becomes yi hat plus xg hat. Okay, so this is different from the previous vector function now. Okay. As a matter of fact, so this one here seems like there's a little bit of rotation in it here actually. Okay. So now this time, what does this vector field looks like now, right? With this change of the vector function. Okay. So you could try exactly the same approach at here. So let's say I give you 1, 1. So if this is your x, y location, okay, so if it's 1, 1, then for this particular vector function, 1 over here, so I hat, and then minus what? G hat. So at the location 1, 1, you have a vector I hat minus g hat. Okay, so let's plot this vector at here. At 1, 1, okay, at 1, 1, this is 1, 1 here. Okay, so we're going to plot a vector at this location. Plot which vector? Plot this I hat minus g hat. So maybe let's plot I hat plus g minus g hat first. I hat minus g hat means x equal to 1, y equal to negative 1. So it actually means you have a vector pointing like this, right? So this vector here is I hat minus g hat. But now we move this vector over to the 1, 1 location. Okay. So we get this vector over here. A vector suppose probably more precisely should touch here. Does that make sense? Okay. So that's how you draw the vector fields, and you can literally come up with any numbers, okay, and then practice. So if you have a negative 1 point, you have a vector of what? X is negative 1, y is 1, so I hat, and then plus g hat, right? So let's find a negative 1, 1 point, so negative 1, 1, so negative 1, 1 is over here, okay? And we're plotting a vector at this location, I hat plus g hat. And you will see the vector will be looking like this, okay? Because 1, 1 is this vector, right? So you move it over here, you got this vector. Okay. So that's how you construct. So plot as much as possible, okay? After you plot it, okay, and you'll see you get a vector like this. It's very much like a swirl of water flow at here, right? Yeah. And far away from the origin, you have a faster speed, something like that. Okay. It's not exactly a depiction of a water flow or something, but it's basically give you a concept. This vector field, okay, representing a flowing of something, okay, in this manner. Okay. Yeah. Good. So try something else. So you can try another one here, as shown in the lecture notes. So now this time, if we use a slightly different vector field, it's negative y I hat plus x g hat. So what's the difference? So this one is y I hat minus x g hat, and this one here, it's a negative of the previous one there. Okay, it's negative previous one. So what do you think is going to happen to this vector field? So if I plot this, if you have this one already, the difference will be simply what? The reverse. Exactly, right? Yeah. So you're gonna get complete reversed direction, okay, of these vector fields. Good? Yeah. I showed you some Maple and MATLAB commands, how you can plot a vector field, sometimes to help you visualize just abstract equations. Okay. And that example, let's look at a 3D one. So this one, I'll start with an expression like this. Okay? So here's an expression, x squared plus y squared plus z squared equal to 4. Okay. And this is a sphere centered around the origin with a radius of 2. Okay. Now this side here, okay, let's call this is f of x, y, z. So this is a function of 3 variables at here. Okay. And now I'm going to calculate the gradients of this vector the gradients of this scalar function f. Good. Yeah. So basically, what I just given here is a function f equal to a constant 4. And if you recall, when we learn multivariable function, when you have a function equal to a constant, that basically represents its concept is called what's called a level surface. Good, right? And then you can calculate the gradient del f. Okay, so you basically get a gradient for the function f at here, and the meaning of the gradient function, as we repeated saying here, it's giving you a direction pointing to the greatest increase for the function f. Okay, right? Just repeat here, and then you calculate del f right here. That's pretty simple. So 2x I hat, 2y j hat, and 2z k hat. So you get this gradient vector, and this is a vector. So let's call this as a vector f at here. And this essentially is a vector function. Right? So you can see whenever you take a gradient of a scalar function, you will get a vector function. And that vector function will generate a vector field. Okay. So this one here, it's a 3D, but you can actually visualize this very easily because we have already visualized a 2D x I hat plus y j hat. Right? Yeah. If I put a 2 and 2 here, so not much difference, except maybe the vector length will be bigger at a certain location, right? Yeah. But if I extend it to 3D at here, just add a 2z k hat here. So now can you imagine what this vector field is in your head? You have a whole bunch of arrows shooting out of the origin, right? As it's much more away from the origin, the length of the arrow will become longer. So basically you're going to get a vector field like this, right? Yeah, it's more like the back of a porcupine, right? All needles pointing out of the origin there. So that's the vector field for this particular one. So as a matter of fact, if you relate to the idea grading vector pointing to the direction the greatest increase for this function x squared plus y squared plus z squared. Okay, so what does it mean? Basically, if I start at this location, okay, that means you have to go to that direction, which is basically reading direction out of the origin, okay, and that gives you the maximum increase for this function here. Okay, good. Vector field is also very useful in terms of visualizing a lot of physical quantities here. So this is a very typical fluid mechanics, aerodynamics testing. If you put an airfoil in a wind tunnel, okay, and then you want to visualize basically the amount of airlift, okay, with respect to this airfoil at here. Okay. So this is the flow of the wind at here. And you can visualize the flow of the wind around this airfoil by plotting a cluster of basically velocity vector field around it. Okay, and you can try to basically derive something based on that phenomenon, based on the observation, right? So that's called essentially streamlines, okay, around this airfoil here. So very useful depiction. It's basically one way of presenting information, right? Okay. So what do we do with the vector field? Okay, we're going to do many things within the vector field. The first thing we're going to do with the vector field is we're going to do this so-called vector line integral. Vector line integral. The keywords at here, what should remind you is before the midterm, we did a line integral called what? Scalar line integral, right? Yeah. So you are integrating basically a scalar function in that perspective, okay, over a certain curve. But this time we're going to integrate, okay, over this, let's say a similar curve, curve C in a 3D space, but with respect to a vector field now. Okay. Let's start with a simple one here. Let's basically introduce the idea of vector line integral. Start with a very simple one here. If we apply a force in an object and we push this object, okay, the force is applied horizontally. We push this object horizontally, okay, by a distance of d. Okay, so then in your high school or even middle school, and the question asks how much work is done by this force. And everybody knows, okay, so F times the distance. Right, that's how much work is done, okay, given this force and this distance. Okay, so now you can easily extend this question slightly difficult level, but this time, okay, this force is not a horizontal force anymore. Okay, so it's tilted by an angle of theta. Okay. And the same target, you push it by a distance of d. Semi questions, and then how much work is done by this force? Okay. The formula not going to change. It's still going to be force times distance. Okay, force times distance. But the force in this case is not a horizontal force. So you need to basically get the horizontal component of this force and then times the distance. Horizontal component of the force. Now this time I'm going to use the vector here. Okay, instead of just the scalar quantity that's usually what you learn in high school, but I use the vector idea. Okay, force is a vector, displacement is a vector. Okay, so if I use the vector concept, then this F at here, right, that's the magnitude of this force, times the cosine theta, that's the horizontal component, and then times the absolute value of the vector d, which gives you the displacement, okay, a distance, rearrange it, so F d cosine theta. Okay, so that's how much work is done under this situation right here. Okay? Okay. And what does this remind you? Dot product. So this is basically F dot D at here. So F dot D. So F dot D give you the amount of work done by this force. Okay, in a more general sense, when the force is not a horizontal direction. F dot D, as we learned, okay, in the first lecture, you can always separate the D into two components. One is direction, the other is magnitude. Okay. And now everything actually makes a lot of sense. If you look at this expression, this simple expression right here, right, what that tell us is, first of all, look at the brackets here. What does F dot D hat tell us? Using a simple language. Whenever you use a vector dot univector, what does that give us? The length of the projection, right, of the vector in that direction. So this is the length of the projection, the force in that direction displacement. And then times the distance, give you the total work done, right? So that's this simple expression here. Essentially conforms with the idea of the work, right, equal to force times distance. Okay, good. Now I'm going to make it a little more complicated, because right now what's simple is this force, when you're pushing away this object over a certain distance, the force we consider is a constant direction and constant length, no change, right? Yeah. So what if I have, okay, and also we're going along a straight line at here. Okay. So to make it more general, so we're going to go along a certain curve C. Okay. It's not a straight line anymore, and it's not a short distance. Okay. It's a curved path. And moreover, let's say we have a small mass starting from this location, trying to push it. A more general is we're placing this small mass m within a force field. So you have a field of force, okay, in the 3D space. Okay. So I don't know how it's exactly going to be, but there's a field of force, okay, existing in the 3D space everywhere. Is that good? Right? So then which force actually matters to this small objects, right? If you have a force over here, it probably doesn't matter, right? Because it's not pushing. It's pushing something over here. So the only force that matters, that's trying to push this object, is a force at this location, maybe this way here, I don't know, right? Does that make sense? Yeah. So basically, as if you try to go along this curve C, okay, if you try to go along this curve C here, for every point on that curve C, okay, because this curve C is within the field, then there's always a force vector at that location. Right? So that force vector is the one trying to apply to the object, trying to push it along this curve C. And what makes it difficult is because the vector function or the vector field can be arbitrary, so the direction of the force at certain location along the curve C will not necessarily always be pointing the same direction or the same length. Okay, so it's a time-varying quantity. Not time-varying. It's a location-dependent quantity. Okay, yeah. So if I ask the same question, then basically the question is, how much work is done? Okay, as you're pushing this, moving this object over the whole curve C at here. Okay, so that's basically the question we're trying to answer at here. The total work done, I should say total work done over the curve C. Okay? Yeah. Okay, so let's derive this formula here. Okay? And we're going to make use of the concept, this simple concept we have just derived here. That's a simple concept over there. Okay. So what I'm going to do is I'll use the approximation approach as we always did in previous lecture. So we're going to let's say suppose here is the location of the objects at here, and we're going to take a very small segment. So suppose you're moving these small objects, the force is moving the small object over a very small segment, a curved segment over the C here. So from here move it over here. Sorry about it, just give me a second. Okay. So what we're doing is we're taking a very small segment here. Typically, for this small segment, we call it delta S, right? But don't write it yet, okay? But typically, we call it delta S. But in this case here, I wanted to relate to the idea of displacement here, not just the distance concept. I'm going to use for this one here, I'm going to use a ds vector, okay? And that makes a lot of sense because when you're at this location, you're moving to a adjacent location, right? You're not just moving in a simple distance, but you're also moving probably change direction, right? So this ds here essentially have two different meanings. One is direction, and the other is the distance. Okay. So if I look at this location, saying then what direction we're moving, then how should I represent a direction? Given a curve, you're moving along the curve. What will be a quantity that you can use to represent the direction you're moving along that curve? Based on what we learned. Derivative, yes. What's the name of that? Not gradient. Velocity, but we call it tangent vector, right? Tangent vector. Okay? So we can use the unit tangent vector to represent its direction. At the same time, you move with a certain quantity ds at here. Right? So that's what ds vector representing at here. Okay? Direction of the curve, which is the t hat, and distance of movement, distance movement at small ds. If you recall this small ds, in the previous lecture, what do we call this? We had a lecture on this. We calculated the so-called what? The arc length of a curve, right? And that's basically depending on this quantity ds there. Okay? And we have a formula which I'll write it down later. Okay? Good. So that's what I mean by moving from here to here, okay, with a ds vector. As you're moving from here to here, what most probably going to happen is that this location, you have a vector, a force vector f at this location. Okay. Now, because we're taking a very small segment, then I can consider from here to here we have a constant vector f at here. Okay. Basically, like from here to here, if this is a very short displacement, then this f will be considered as a constant. That make sense? Right? Then for this ds, okay, over this ds, okay, over the ds, there will be small amount of work done, right? Very small amount of work done. Then how much small amount of work is then based on the formula we have derived over here. So if you have a constant f moving with a small distance d, then the work done is f dot d. So basically in our case is what? F dot how much? The ds at here. Okay, that's small ds, infinitesimal ds over there. Okay, so this is how much work done over, okay, that little area, the little segments. Okay. And this quantity here, I can rewrite it, so dw equal to f dot t hat, and then ds. Good. So basically, we have derived a small amount of work done over a small segment of a distance. What we're looking for is the total work done over the whole curve C. then guess what do we do? All we need is just integration of both sides. Okay? When you integrate the left side, integrate d anything, give you back that whatever. So then this part is the work at here, so you get total work equal to f dot t hat and d at here. So we're integrating over this curve C. So basically what we have just done is we derived the formula for vector line integral. Okay? Yeah. So vector line integral is a pure mathematical concept, but what we have just approached it, the way we approach it is we give it a meaning, the total work done, right, over certain lengths of curve C, and within this vector field F. And your vector field F not necessarily is going to be just a force vector. It can be any kind of vector, basically, vector field. So what do we do? How do we calculate this one here? There's a lot of symbols involved at here, right? So let's simplify this and try to get idea of how to calculate this. First for ds, okay, so this is something we have done before. ds is basically dr over dt dot dr over dt times dt. Okay, it's not a dot times dt. That's your small arc length formula, okay, ds. And if you integrate this ds, you get a total arc length. And this one, alternatively, you can write it when you have a dot product between, when you have a, basically use the same vector dot itself, you basically add a square root, you basically get the length, okay, of this vector. So that's your ds equal to dr over dt, and then times dt, the absolute value of that. Okay. And t hat, okay, we also learned in previous lecture, this is a unit tangent vector. So to calculate unit tangent vector, first step, you calculate the derivative of this parametric equation for the arc for the curve C. Then you divide it by its magnitude, okay, and that gives you this unit tangent vector. So now I can put things together now. So put the t hat back here, put the ds back over here, okay. Then the w, okay, equal to vector field f, okay, dot t hat, and t hat is dr over dt, dr over dt, okay, that's your t hat, and ds is dr over dt dt over the curve C. Okay. Okay, so that's putting things together, and you fortunately you can cancel this denominator and numerator, which are the same. So we end up with CF dot dr over dt and then times dt. Okay. Alright, so that's basically one formula, and as you're going to see, there this vector line integral can be written in a slightly different format, although they're all referring to the same thing. But this is number one. So this is the first, how they look like, okay, like this. Yes. Yes, you can. That will be the second how it looks like. Yeah, second type. So if you cancel this dt, okay, you'll get this, right? Yeah. But I need you to point out the difference here, because I noticed in the past a lot of students don't know the difference. What's the difference between this and this? Well, technically no difference, but when it comes to the computation, some potential mistakes could happen. For example, if I give you r of t equal to t I hat plus t squared j hat. Okay, yeah. If you have a vector, a curve C represented by this parametric equation, okay. So now you're required to do this vector line integral, okay, using the formulas. So if you choose the first one, okay, that's typically what you do. You won't make a mistake. If you choose the first one, you do the derivative dr over dt, and you get basically I hat plus 2t g hat. That makes sense, right? So you plug it over here, and then times dt, and you do the rest of the integration. Okay? Yeah. If you choose the second one, so what's dr? So the potential mistake a lot of people make is they still write this. They still write it like this. But technically you should do what? The whole thing times dt. Okay? Yeah. Because you cannot you cannot do the integration without dt over here. Right? That's your dummy variable. Still need that to do the integration. Okay? So depends on your comfortableness. Pick whatever formula that you can use, but however use it appropriately. Okay. Okay. So coming back to this formula here. Okay. I want to emphasize again. Always remember we approach with a specific example, but when you're solving this kind of question, you should bear in mind this is a general mathematical concept. This is basically a vector line integral concept. So F here can be a force vector field. Okay, and if I give you a completely different field, maybe, right, I'll give you so basically, or maybe a velocity field is given. Okay, velocity field like that, and the airfoil placed in the wind tunnel. Okay, so around the airfoil is the flow of the wind. Right, that's velocity field. Basically, you use a different symbol now, right? Maybe use a capital V, okay, representing this vector field. Okay. And then what you calculate maybe is v dot t hat and a ds. Okay. That's just the same concept of vector line integral. Okay. Yeah. Now, actually, interesting. The same basically the same picture I showed you here. If you have an object with a certain geometric form, okay, then you have basically a closed curve C here, right, around this object. So you could do a vector line integral like this with a symbol circle. So this circle here basically means this is a closed curve C, okay, closed curve C. So we can do a vector line integral around a closed curve C, integrating this vector field over the curve C. And we can use a symbol gamma here to represent the results of this integration at here. Okay. And there's a name associated with this kind of integration. So this name at here, we call it, it's the circulation, okay, around this closed curve C. Okay. Circulation. So circulation for what? If you look at this integration here, it's a circulation of the vector field, okay, but it's not purely just the vector field. It's actually because you have a constraint curve C here. It's this dot product, the v dot the t hat, right? It's the projection of the v at a certain location on the curve C, projected to the t hat location, right? That's what's circulating at that location, right? And then you add all them up, you get total circulation around this curve C. Okay. And in a simple aerodynamic here, there's a simple formula called L equal to rho u times gamma, and rho representing fluid density, okay, and u representing the flow, the airflow velocity, okay, the speed of the body relative to the airflow velocity u, and then times this circulation gamma at here, okay, and you got the so-called lift force. Okay, so see that simple vector line integral, it can give you a very important actually formula. It's called the Kuta-Joukowski theorem. So anyway, if you're interested, we have aerodynamic course offered by one of our professors in the 4th year. Right? Yeah. So let's look at a couple of examples, okay, and you'll see the computation-wise, okay, is very much like the scalar line integral, okay, except here what's involved is vector field. Okay, let's make it a little bit different. I'll use a 3D vector field, okay, to represent, to calculate the vector line integral. Here's a 3D vector field. And then the curve C, represented by a parametric equation. So Ti hat, Tj hat, T squared, T cube, K hat. The T goes from 0 to 2. And I want to calculate the vector line integral over this curve C. So I'm choosing this second notation here, but bear in mind, this is exactly the same as this expression. Okay, let's do the calculation for this simple one. Okay. First, we need to calculate dr over dt. Okay. Once you're comfortable, you can always just go along without do this each steps first. Okay. Dr over dt, we get 1, 2t, 3t squared. Dr over dt. F function, okay, is x, y, z. Okay. Here is a vector function, right? So what do we do with the x, y, z? It's a very similar idea. This is why I want you to look at your midterm, the second, scalar line integral question, right? Yeah, second question. So basically, you need to replace your x, y, z with the parametric equation or the coordinates on the curve C, x of t, y of t, and z of t. So in this case, we're going to replace the y with t squared, replace the z with t cubed, replace the x with t. Okay. So with this replacement, you're going to get t to the power 5 I hat, and then t times this, t to the power 4 j hat, x times y, t to the power of 3 k hat. In the scalar line integral, you replace the scalar function x, y, z with x of t, y of t, z of t. And here we're replacing this x, y, z for the vector function. Coming back to the original vector line integral, putting everything into here, so you have a t to the power 5, t to the power 4, t to the power 3, dot 1, 2t, 3t squared dt. The range of the t goes from 0 to 2, as the question says here. So 0 to 2. Calculate the dot product. T to the power 5 plus 2t to the power 5 plus 3t to the power 5 dt. So you've got a 6t to the power 5, and this simple integration will yield a 64. Okay. Any questions so far? Okay. All right, let's take a look at another example. Okay, and then we can move on to a different concept. Okay, so here's a different vector field, very similar, but I wanted to actually show you the third type of notation wise for this vector line integral here. Okay, so what does this equal to? So for this vector, for this example here, essentially this is how it looks like. The red one is the vector field. I think we have shown that. Okay, counterclockwise. And then this is a curve C. Basically, it's a y equal to x squared, the curve C. Okay. So place the curve C in this vector field and integrate this vector line integral and see how much that is. You can do exactly the same process as we did in the previous example. Okay. But I wanted to show you another, basically the third type of notation. So the f at here basically is equal to this mi hat plus this ng hat. It's very much like this. So f equal to mn. So we're using 2D to illustrate. And then you have the dr over here, right? The dr. So dr, technically what dr is, basically you're taking differential dx and differential dy. Okay? So we should probably x of t here and y of t here. So you see here, this x of t is t, this y of t is t squared. In this case, you have a negative y and then x. Okay. And in this case, here's a t, so t squared. So you get 1, 2t, and then times dt. Right? Times dt. So basically, dx equal to dt, and dy of t at here equal to 2t dt. Okay. So now I'll start from here. Okay, start from here. C f dr. I'm gonna put this m n over here. Dot dr. So dx of t, dy of t here. Okay. I put it on C. Right. That's the formula. In the previous example, what happens is you replace the mn over here, and you place dx dy over here, and then you do the dot product. So you could basically over here m dot dx of t first plus n times dy of t here. So you see, basically this is another appearance of this vector line integral here. So you could write down this integration c m times dx of t and plus n times dy of t. Okay? Yeah. So in my case, I can keep writing it here. So m is negative y and dx, and then n is x and dy over the curve C. So now I'm putting everything together now. Okay. dx, as we've shown here, is dt. And y, you replace the y with the y of t at here, which is t squared. Okay. And it goes from 0 to 2, of course. And plus the second one here, x is replaced with a t, and dy is replaced, as we did, 2t dt. Okay, so that's everything in here, right, for this integration. So everything is in terms of t now, and you can do the integration. This is combining things together first, maybe, and you get 8 over 3 for this vector line integral. Okay, yeah. So this is not a very common one here. I encourage you to maybe use the first two notations for vector line integral, these two here. Okay? Yeah. But you can certainly, this is also one of this kind of, one of the formula, how it looks like. All good? One more example, then we can move on from this vector line integral. This one here, I don't need you to calculate. Okay, most probably I want you to actually observe and then tell me what it is. Here's a vector field, right? Basically x, y. And curve C, instead of giving you as a parametric equation, so this time the curve C given to you is basically a circle, okay, around center with a radius of 8. And let's call it counterclockwise. So imagine this is a counterclockwise curve C. That's your curve C in here. Okay, so question is, what is the vector line integral f, okay, dot this dr at here? Okay. Now before you dive into the computation or even think about how to calculate it, okay, this question actually you don't even need to calculate. You can actually tell the answer right away. 0. Why 0? Exactly. Right? So, remember the other formula for the vector line integral, right, is f dot t hat dx. That's basically the most original formula, right? F is the vector field. T hat is the unit tangent vector or the direction of the curve C. So let's take a look at this one here. If I go in counterclockwise, then the t hat is always a tangent vector to this circle, right? And then f is xi hat plus yg hat. And that is a vector we plotted actually, right? You know, remember the vector field we plotted? It pointing outwards, right? And from the origin basically. So for any point on the curve C, you have a vector basically pointing outwards, okay, to this to the curve C. And this is naturally a perpendicular relationship. That means f dot t hat is always equal to 0. So you don't have to do any calculations. You can just write it down. It's equal to 0. Excellent. Okay. Now, what if you really want to do the calculation? Then what do you do? Right? If you don't believe it, so I just want to do the calculation. What am I going to do then? The circle C, what you have to do is you have to come up with the parametric equation for the curve C first. Okay. And in this case, it's going counterclockwise, and that will be your parametric equation for the curve C. And then you basically start from here. You follow exactly the same procedures, okay, as the other two examples. Okay. And you will find the answer is 0. Okay? Okay. Okay, so those are all about vector line integral now. Okay. I don't think it is computational wise, it is very difficult. As long as you're comfortable with the idea of the parametric equation representation for curve C, and also how to do a substitution for the vector function f, okay, given the parametric equation for the curve C, and then the rest of the work is just dot product and then integration. Okay, so next concept is conservative field. Okay, conservative field. Now there is a very special kind of field. There's a very special, I should say, vector field. Okay, special kind of vector field. Okay. And this special vector kind of field is the so-called gradient vector field. What is a gradient vector field? Basically, if you're given any function, okay, any scalar function f, it could be a 2D function f, it could be a 3D function f, or in 4D, whatever, right? And you can always calculate this del f. If you have this function, scalar function given, you can calculate its gradient vector del f. And this del f itself creates a field. Right, so as I demonstrated using this example here, the this spherical surface, if I calculate the gradient, I can create a vector field, right? Yeah. So this gradient vector field is what we call this. It's a special kind of vector field, and it is called conservative field. Okay? It's called conservative field. Can you give me an example of a conservative field? No? Where are we living on? Gravity. Not just gravity, it's called gravity field. Right? Gravity field is conservative. Why is it conservative? Or what do we mean by conservative? Where did all the first year of high school physics go? Conservative. If I move an object from here to there, but going from along a different path, does it matter to the total amount of work done? Right? That's what we mean conservative. And when you have an object in the 3D space, in a gravity field, that object always have a so-called what? A potential energy, right? Yeah. So gravitational field is a conservative field. So here is a couple examples here for you. Okay. Yeah. So let's come back to the greeting vector field first. So I have F equal to the del F. Okay? F equal to del. So I sometimes keep shuffling between an actual example and the pure mathematical expression, right? So coming back to this greeting vector fields here. Okay. So let's think about the relationship now. Okay. So this is basically a conservative field. Okay. This is essentially a conservative field, and I'll show you why. Okay. Next, we'll show you why. For now, just recall this is conservative field. And one nature of the conservative field is path independence. Okay, path independence. And this small f at here, small f at here, we give it a new name. It's called a potential function. It's called a potential function for this vector field f, or the conservative field f. Good. Okay. So those are pure mathematical names here. Okay. Yeah. And in math function, there's a function just called potential function. It is a very useful terminology in physics, in engineering. Yeah. It's called a potential function. Okay. So a couple examples here. Gravitational potential. Okay, gravitational potential. Gravitational potential is equal to this. So V equal to G times M over R. G is the gravitational constant. M is the mass of the planet, okay, or Earth, or any other planet. And R is the distance from the center of that mass to the location of the object. Okay. So this is called a gravitational potential. So this V here is basically the potential function. Now if we do a greetings calculation, okay, for this vector, for this gravitational potential function, okay, more precisely, we in a notation wise, we add a negative in front of it. Okay, we calculate this negative greetings V. We get the so-called gravitational field. Okay, so this is your gravitational field, and the calculation will yield negative G M over R square and R hats. Okay, that'll yield a vector field. And R vector is basically the vector representation for any points, okay, in the 3D space. That's the basically position vector, right, to that point from the center of this big mass M. R hat is just the unit vector of this, right? You divide it by its length, you get the unit vector. Okay. So that's gravitational potential. And in your electromagnetic field, we have this electric potential. And the electric potential here is, the function is this. So if you have a point charge, you can write it down as this. This is your electric potential. So that charge Q over 4 pi epsilon R times the distance. Then you can calculate, okay, you can calculate to get electrical field. E. Okay, electrical field E, and E equal to del negative del, okay, phi E. So negative gradient vector of the potential function. So that'll give you Q over 4 pi epsilon 1 over R square and R hat. Okay, R square R hat. Okay, so that's a couple of examples: gravitational field and electrical field, okay, or gravitational potential and electrical potential. Yeah. All right, so the next question is, so what's so special, right? As I mentioned, it is very special, but then why it is special? I think I answered the question, but let's show that and prove that. Understand what is the special parts about this conservative field. Okay. And the next thing I'm going to show you will definitely be tested in the final exam. So you hear me that, and then you've got to be vigilant about what we're going to learn next. Okay. We have a very important theorem. Okay. It's called the fundamental theorem of calculus. Okay. Fundamental theorem of before I finish here, when you see the way of writing up to this point, fundamental theorem of calculus, I actually should remind you, what's the fundamental theorem of calculus? Sorry? Differentiation? That's right. So if you have a integration from A to B, this equal to the subtraction of the antiderivative at the B location minus its A location. Right? That's fundamental theorem of the calculus. But this is not what I'm going to write that here. What we're going to write here is a fundamental theorem of calculus for line integral, more precisely, vector line integral. Okay? Yeah. Okay. I'm going to read this one here. This is not a cause confusion. This is not the theorem we're going to write it here. Okay? Yeah. So what does this theorem says here? So here's what it says: given a curve C, okay, going from P0 to P1. Okay, so basically this is what it means. The curve C starts at P0 and finishes at P1 point. Okay, suppose the corresponding t value maybe is A to B. Okay, so when t equal to A, the curve C is at a point P0. When t equal to B, the curve C is at P1. Okay, so basically we have a R of t, and t goes from A to B. And there is a vector field F, okay, exists in the 3D space. So you have a vector field exists in 3D space. And this is a special kind of field, as we pointed out. It comes from the gradient operation of a scalar function F. Okay. So those are the given conditions here. Then, okay, if you're required to calculate, the vector line integral, okay, over this curve C, integrating this vector field over the curve C. So technically, we just have to replace this vector field with del F. That's how it comes from. Dot dr. Right, that's basically what you're required to calculate. But because this is a very special field, then you don't need to actually calculate this vector line integral. All you need to do is you do this here. So basically this vector line integral, what it means is, okay, it equal to the value of the scalar function f at the p1 minus the value of the scalar function f at the p0. You see the similarity between this one and the fundamental theorem of calculus, right? The fundamental theorem of calculus is the antiderivative at the b minus antiderivative at the a value. Here is the potential function f at the p0 value, p1, minus the potential function's value at the p0 here. Okay. Yeah. And this actually tells you immediately the concept I told you, path independence. So essentially, if I have a vector line integral f dot dr and then del f, right? The f comes from del f. So, and then if this is what it equals to, if you look at the final calculation at here, between p0 and p1, I can have maybe a curve C, completely different kind of curve C, right? And this vector line integral, and this value here from p0 to p1, the calculation, it's completely path independent. Right? It doesn't depend on the form of the path. It only depends on the starting and the finishing points of the curve C. Okay? So basically, this is what we call the path independence. Okay. So still have a couple minutes here, so let me show you the quick proof of this. It's very simple proof of these things that are here. Okay, I think it's important to show you the proof for this one. I don't normally do a lot of proof because this is a very important theorem. So C at here is R of t equal to x of t, y of t, and z of t. So we're using an arbitrary expression for the curve C. And t goes from a to b. Okay. Let's calculate this line integral. Okay. Let's take a look at what would that be. Okay. It goes from a to b, and del f. Okay, del f is whatever that scalar function is. You can calculate its greetings, which is basically 3 partial derivatives. And then dot dr, so dr is basically dx over dt, dy over dt, dz over dt times dt. Okay. So that's what happens at here. And now we can multiply this dot product out. So we get fx dx over dt plus fy dy over dt plus fz dz over dt times dt. Multiply the dt into it, you can cancel all of the dt out. Okay, then you get fx dx plus fy dy plus fz dz. Okay. So, what does this remind you? When you have a fx dx, fy dy, fz dy, total differential, right? This is a total differential at here, then a to b. So when you're integrating d anything, remember you get what? You get back this f at here, right? You get back this f. And this basically means your f at t equal to b minus the f at t equal to a, which is essentially the f value at p1 minus the f value at the p0. Okay. So that's the proof. Okay. As I said, this is definitely going to be tested. Okay. But the trick is you will not be told to use this to do a vector line integral. So you have to be able to identify to use a vector line integral. This theorem, this fundamental theorem. Often in time, when you're required to calculate, let's say, calculate this vector line integral. If you don't use this theorem, you will never be able to get an answer. But if you use this theorem, you can get an answer right away. Right? So that's why you have to be able to identify it. How do you identify that you can use this theorem? When this f is equal to this. Is that clear? Okay. So we'll emphasize this a little bit later, but just for now. Okay. Yeah. Okay. Any questions? Thank you.